Oh.
Can you hear me? Cool. All right, so welcome to this last-minute presentation about Servlet 3.1 Asynchronous I/O. So just as a quick poll, who's ever heard about Servlet 3.1 or even using it? Who's using it? Almost no. Okay. So we're going to have a lot of fun because I'm going to show you some code, and we will, go through an history of how the Servlet 3.1 expert group came up with the Servlet Asynchronous I/O API. It's a very interesting process how they came up with the solution that they came up with. But the key point is that asynchronous programming is really hard, and it is very difficult to find good APIs. And we will see why that is. So who am I? My name is Simone Bordet. I work for an American company called WebTide, which has been acquired by another company called Intalio. And I work on the Jerry team. These companies employ basically the Jerry committers, and we provide services around Jerry and anything you might need. Who knows Jerry here? Almost all of you. Well, it's a server container, basically. It's you could call it a direct competitor to Tomcat or any other server container. But we like to be like on the edge. We were the first to implement the speedy protocol. We were the first to implement the HTTP2 protocol. We have our own website over the HTTP2 protocol served since months. And tomorrow I'm going to give a more detailed talk about HTTP2. And so if you want to come, you'll be welcome. So why async? This is the agenda, basically. We will see why we want to go async and why async is now pervading basically every application, every framework. And if you don't have async in this word, then it's not even worth looking at it. And we will take a look at the evolution of the Asynchronous API, and we will see a number of examples of how this API can be used and what are the common errors that you can actually make in using these APIs. So why async? Well, this is the main issue. This is a normal interaction diagram that you have between a client and a server and a third-party services, like, for example, a relational database, right? So the client makes a request to the server allocates a thread, which is this blue bar here, and then in allocating this thread makes a request to the relational database that takes time to perform the query and return the results. So the database is doing its job, it is returning the results, and while the server is waiting for the database, this thread is allocated. And even if it's doing nothing at all, because it's just waiting for I/O, this thread is not used for anything else. It stays there and waits for I/O. It cannot serve other requests, it cannot be used for anything else, all right? So, and then when we have the response from the database, we just return the response from the client. Kind of easy. So this is called blocking wait. And because of course, the server, this thread in particular, it is blocking, waiting for the database to return, right? So why is this bad? Because every time we have a thread allocated on a server, it consumes resources. It allocates a native thread on the operating system. It consumes memory because every thread that you allocate on the Java JVM, it occupies 1 megabyte of space in the operating system, in the JVM, sorry, for allocation of the stack frames for that thread. And of course, you have OS scheduler and data structures, and you have thread locals that might be associated with that particular thread. They are not released until that thread goes out of scope. If it is blocking, those thread locals will still be there and consume memory. And of course, you have local variables in that stack frames that will be there for the whole duration of your database call. Like if you have many stack frames, many local variables, all those variables are alive. They cannot be garbage collected, and so forth. So basically, blocking waits consumes a lot of resources that are expensive. So what we really want is this. We want to be able to say, okay, the client makes a request. We set up something here that makes a call to, for example, a REST service. And then we want to return this thread to the thread pool. And, you know, the thread is now waiting, but it's not waiting blocking, it's waiting in the thread pool. And that thread could be reused to do something else. For example, to serve other requests or something. We'll see a few examples. So this scheme is called StWait. And when the response from the third-party services returns, then we allocate again a thread here. We compute the response to be sent to the client, and then we write the response back to the client. So, okay, what do we gain if we go to this model? Well, this is one possible thing that we can do, right? So imagine you have to make two calls, one to a NoSQL database and another one to a REST service, right? And you want these two calls to be concurrent, parallel. You don't want to go to the NoSQL, wait for the NoSQL to return, then call the REST service, right? You want to go in parallel and do the two things together. How would you do now? Well, you take the thread that comes in with the response and that does one thing, and then you spawn a new thread and the new thread does the other thing, right? However, if we go async, there's no need to do that and spawn a new thread. We can use the same thread to actually, you know, make the request to the NoSQL, then returns immediately because it's asynchronous, and then we can immediately afterwards do the request to the REST service and immediately go back to the pool and do something else again, right? When the two responses come back, we again allocate a thread for a moment, compute some data structure or response, and then we send the whole thing back to the client. Okay? So if we go async, what we can do is that with the same thread, we can do multiple parallel operations. All right? Or, what is the other thing that we can do? Well, we can actually serve more clients because, you know, first client makes a first request, then this thread goes back to the pool. So the same thread is picked from the pool again, and it can serve another request from a second client, and then it goes back to the pool, gets picked again to serve a third request to the client for another client, right? So not only we can do multiple things with the same thread, but we can serve multiple clients with the same thread. Well, what do we get? We get that by doing this, we improve latency because we're not dispatching new threads or something, we're using the same thread. We can do more things with less resources. We can use better the resources that we have, and this means that basically StWait use less resources on the server. Less resources are used in a more efficient way, and therefore you have increased performance because you have reduced latency. And increased performance on your web server means more money. This is something that will come back tomorrow as well for HTTP2. But here there are a few examples that I will, mention again tomorrow in more detail. That of big web services that basically had very good returns by increasing the performance of their website. Like I'll just cite one, Mozilla.org. They cut off 2.2 seconds from the main page. That turned into 60 million more downloads a month or per year, of the Firefox browser. Just shaving 2.2 seconds on the home page. 60 million Firefox more. So for them, it's a lot of money. Like it's real money, it's millions probably, okay? So it's really important. Just to emphasize this even more, this is a demo that we have online at this address, webtype.com/async-rest. And these are the behaviors of two web services call. Like on this column here, we're calling a web service with the keyword kayak, and we do it in a blocking way, and we are doing in a non-blocking way, all right? This one. So as you see, it takes 200 milliseconds to return the result, and also here. So it doesn't change much, like 200.4. So basically, the time, the dominating time is the network round trip, okay? Make request, and the time to go to the server, to the third-party server, in this case was eBay or Amazon, I don't recall, to make a request, and then return the results. Takes 200 milliseconds to go from our server to the Amazon.com server, right? And we just make a single keyword. Now, the behavior is different though. It's being read and therefore blocking. We had a thread allocated for 200 milliseconds in the first case. In the second case, turns out that the thread was allocated for just 1 millisecond. It took 0.9 to get the request prepared at the beginning, and then it took 0.1 to generate the response back to the client. So basically, we had 199.5 milliseconds of free time. It means that this guy, in that same period of time, could have served other 200 requests, or it could have served 200 other clients concurrently, while this guy needed 200 threads to do the same, right? So if we get 200 requests concurrently at the same instant on the server, here we would need 200 threads. Here, we just go by with one thread. Okay, it's a big difference. It's 200 times factor of difference in performance. Well, but not only this. This one is a multiple query for these three keywords, and they're made in a blocking way. So we ask for the first, ask for the second, ask for the third, and we stay there for 600 milliseconds, blocked, right? If we make this asynchronous, well, it takes less than 300. So we actually shaved that for the same task. We are now doing the same task in less than half of the time, just latency-wise. And of course, in the same way, we take very few time to actually block and use a thread, and all the rest of the time that we're waiting, it's just free time. That thread could be back in the pool and serve other 278 clients or whatever, right? So there is a big, big, big difference if you go async. This is what makes a service scalable. Okay, so think for a second, how would you use this? If you go to Amazon, AWS, like you have your service into Amazon, and you need 200 threads to serve 200 clients, Imagine what kind of machine you have to allocate in the Amazon AWS to allocate, I don't know, 20,000 clients for your website, right? You need big machines. But with this one, you can go by with a machine that only uses very few threads, and therefore it can be a much smaller machine that actually does this job. Not even does the same job, it does it even better because it takes only less than 300 milliseconds versus 600 here. So that turns directly into saved money, which means more money for you, for your business. That's the reason why Async is going everywhere. Not because it's a hype on the technology, but because it makes money to people. So that's a really good reason to do that. And of course there are technical reasons as well, like for example, in the recent years, all the processor went multi-core, and we really want to use those multiple cores that we have. I mean, we have 8 cores in telephones right now. So in Service, we have 64 cores. So we really want to exploit all those cores at the full level. And we need a way to manage and make this really, really interesting, right? In a very interesting way and a very efficient way, especially. And the other thing is that asynchronous programming, programming is not really new. I mean, the capability of forking a new thread is a capability that every basic operating system has. However, it is very difficult to write asynchronous code. That's why only recently this kind of programming model came up very importantly. And of course it came up and they soon realized, well, threads are good, but you know, the programming model kind of sucks. So new programming models came up, like actors. For example, the ePOL API in the Linux kernel were created to perform asynchronous I/O in that way. Right now there is an effort to standardize what they're called JavaScript promises, which is, you know, a way to write JavaScript code in a way that it doesn't put you into what's called the callback hell. Have you heard about this term, callback hell? Okay, it's a way where you actually have a synchronous operation, and a synchronous operation take a callback to be executed. And you know, when they're done, they call this callback and say, yeah, I'm done. You can do something else now. And of course, if you chain multiple operations one after the other, then you go deep in nesting these callbacks, right? Because you make a first operation, then a callback is called. From there, you make another asynchronous operation that takes another callback, and then you go nested one more level. When that callback is called, you need to write another operation, and then another callback, and you go nested, nested, nested. As we will see, this is going to be a really important problem also in the Java world. And based on these new asynchronous capabilities, new products have born, like Nginx is a fully asynchronous I/O server that is basically trying to replace Apache, because Apache is a blocking one, right? So it doesn't scale as well as Nginx does. Even in the JDK, we got a synchronous API. In JDK 8, now we have this class called completable future, and you can actually write asynchronous code in this way. You can say, okay, I want to supply async, which means start this in a new thread, and what it is being started in a new thread is fetch a query from a REST service. Imagine you have a REST service that returns you back a query, like a SQL query, okay? And then you gotta take that query and send it to a NoSQL database, okay? Because the REST service builds the query for you, knows how to build the query, and then you have to send the query down to the NoSQL database. And then the NoSQL database is asynchronous as well, and then you gotta wait for the result. And the result, what do you do when you get the results from NoSQL? Then, well, you gotta to update some UI, for example, in JSF, or log some stuff, or send back a response to the client, right? So you write it in this way. It's a chained JDK8 typical Fluent API, and the good thing is that you read it from top to bottom, and it's very good because you know that this one is going to be executed first, then this one, then this one. They actually follow the order you write them. Which is very good. It's a very good thing because our brain, it is built in a way that it reads sequentially. It can't read like here and there, right? And we have this wiring where if we read something before something else, then we think that that happens before what we read next. But that's not the case for asynchronous APIs or asynchronous code in general. So we have this new model that is coming up. And this is an important thing though. Once you choose the model, you gotta stick with it. If you try to mix different models, then you're going to end up in problems, okay? Or you have to manage the additional complexity. So let's take a look at Servlet 3.0 and a typical request, a synchronous request in Servlet 3.0. Servlet 3.0 added the capability to suspend the request and response processing, okay? So what you could do was this. You could get the request and call start async. Start async would say, oh, okay, if you return now from the doGet method of a servlet, I'm not going to send the response to the client. I'm going to, stand still and wait for you to tell me when to send the response to the client. How do you tell the container, hey, I'm done, I want to send the response to the client? Well, you call this API, you call context complete, and say, okay, I'm done, send the response back to the client, all right? So this is a typical asynchronous call to a REST service that returns a JSON, all right? So let's imagine that this method returns a completable feature, then we call, then accept, okay, we got the JSON back at a certain point in the future. When we get it back, then write it back to the client, and then complete the response and say, we're done, all right? So the actual execution is do get the output stream, start async, do async rest, which does something, and then we return. And we are out of do get, all right? Then, at a certain point later, this guy gets called, this lambda here gets called, so we write from a different thread, we write the stuff to the client, we complete the response done, all right? Okay, so there are two requirements for this code to actually work fine. The first one is that do async rest must not block. It must be a truly asynchronous call, otherwise there's no point, right? If this method makes an asynchronous call, even if you spawn a new thread, what happens is that the thread, the request thread that enters returns immediately, but then you have another thread that is blocked there. So you just move the problem to something else, to a different thread. Not a big solution. The second requirement is that whatever is being done here in this lambda that comes back also must be asynchronous because, if I'm going to block here, imagine you have like a huge JSON to send back to the client, right? So if write blocks, then I have a thread blocked doing I/O, and again, I'm consuming a resource that could be used for something else, right? So it's not good again. Okay, what kind of API can I use for doing asynchronous stuff? Well, it turns out JDBC, you can't use it because by default is a synchronous API, so you can't call a relational database using a synchronous API. It doesn't make any sense because the JDBC call will block until the results from the database is back, right? So not good. Input stream and output stream, by definition, they're blocking. When you call input stream read, you block until you have content. When you call output stream write, you block until you have written it all, right? So you can't use those. What you can do is you can use a synchronous I/O API, like for example NIO2, files and sockets, or REST client. REST has clients that are asynchronous, although the API kind of sucks. And you can call other servlets that that are asynchronous, right? So what is the problem with this code? Well, the problem is exactly here. This one is an output stream. So when you call write and you have to write a huge JSON back, it blocks, right? Until it's done. If the client is in a very slow connection and doesn't read fast enough, you start writing, then you fill all the buffers in the network path between the client and the server, and when those buffers are full, then you block. right? Until the client slowly can empty those buffers, and then suddenly the server can say, oh, okay, now I can write a little bit more. Then you write a little bit more, then you block again, because the server is faster than the client. And you block again, and you block again, and you block again, until finally you can write it all, okay? So it's not good. This is the main reason for Servlet 3.1. We wanted a way to do asynchronous I/O, all right? Main reason. Everybody is moving asynchronous, and what good we are if we only provide blocking API to do asynchronous stuff, right? It's not good. That's why, in a parenthesis, I think that we strongly need a synchronous JDBC API, which we don't have, but there's apparently no effort for this yet. I don't know if providers or database providers, vendors are lazy, or I don't understand why this is not happening, but we'll see. So, key point for 3.1 was Async I/O. Thank you. Okay, so the expert group sit around the table, a virtual table, and started discussing it and said, okay, what do we use for this new API that we're going to put into the servlets? Do we use Java util concurrent feature? Well, no thank you, because, well, Java util concurrent feature is not really asynchronous, it's just delayed blocking. You can't really do anything with a feature, okay? You can start something, and then what do you do with the feature? The only thing that you can do is to call get, but that's blocking. Now, quick question for you. Let's see how many get it right. You know, feature has a get version that takes a timeout parameter, right? So, if the timeout expires and throws a timeout exception, do you think this write is aborted as well? Yes. Who says yes? No. Who says no, the write is not aborted? Oh, come on.
Well, I don't know.
You don't know. Exactly the point. The API for Java util concurrent feature is really bad, with all the respect that I have for Dagly. But this API was actually, I think, a mistake. It does too many things. You can cancel things, you can wait for things, you can blocking wait, but the true thing that you really want is a Scala feature, something that you can attach a function that gets called when it is completed. Okay? A callback, in other words. So, yeah, so they said, no, let's not use feature. You have a question? Sorry? Guava feature, yes, it's an equivalent version of the Scala feature. I mean, they are kind of equivalent. I think it's called listenable feature in Guava. But yes, that's the right abstraction that we want, exactly. So they discarded feature. Of course, they can't import Guava into the JDK for the Servlet API, but they can do something similar. But then they say, well, let's go something a little bit deeper, because in the JDK there are other asynchronous API, and let's look at those, right? So JDK 7 introduced this new NIO2 classes called Asynchronous Socket Channel. Did you know about them? Okay, a few. So these new classes work in this way. If this is an asynchronous socket channel, then it has this write method that takes what you need to write, a context object, which could be now, and then they take a callback, basically. It's called completion handler, right? This callback will be called when the write is actually completed, and will return you how much has been written and the context object that you passed here, right? And then, of course, you can say, well, now I'm done, so let's finish it. This is a simplification. This is not even true. I mean, here you get an indication of how many bytes you have actually written. So here, if you have like 1 megabyte of JSON bytes, here you could be called with written 1. So here, inside here, what you have to do, you have to, oh, wait a second, I haven't finished yet, so I gotta write a little bit more, but now skip byte number 1 and start from byte number 2 to the end. So it's a really messy API. It goes even worse, because the API itself forces you to do an allocation for every write you make. Now you may think, oh, come on, an allocation with garbage collection these days, who cares, right? Well, it turns out that if you have 20,000 requests per second, this is going to allocate 20 times 20K objects per second. It's a lot. And they're not that small because they're most of the time anonymous in their class. Their context basically grabs all the context that you have around here. So, not really good. Plus, they're not a lambda. They have two methods. Plus, they're not thread efficient because the contract with the asynchronous socket API is this. I'm not going to call, the JDK doesn't call these methods in any thread, or maybe even the calling thread that initiated the write. These guys must be created with their own thread pool, and only the threads from that thread pool can call these methods. So imagine you have to write 1 byte. You can say, okay, write, that completes immediately because you're not stuck in writing, and then that same thread could immediately call this method. Right, completed, because I'm done. I mean, I have almost nothing to do. But it doesn't happen in this way. There is a new thread that gets dispatched to a thread pool. The thread pool may be busy, so eventually, sometimes later, your thread gets to run. It runs on a different core, where all the caches for that core are completely cold. They have to grab back the context object reference and, warm up all the caches, which makes a lot of cycles in the CPU. Finally, it can call this method and complete your stuff. Furthermore, it has this big problem. They are prone to Stack Overflow. This kind of, when you use callback, you always have to watch for Stack Overflow, because what can happen is this. Well, a thread calls completed. Here, what do? Well, if you're not done yet, you write again, right? And you pass again a callback. So you go nested. Right? And what happens is that, okay, I wrote a few bytes, and now it's one of my threads. I can use that same thread to call you again. So you call this method again, and you write a little bit more. So you have completed, write, completed, write, completed, write. You can see where we go. It's the same thread, and now the stack grows. Completed, write, completed, write. Okay, so what is the solution that the JDK smart guys came up with? Well, let's add a thread local counter. When we arrive to 16, we dispatch to a new thread. So that's the current solution. It's a system property that you can configure whose default value is 16, and it dispatches here. It says, okay, am I at 16? Okay, so instead of calling completed in this thread, I'm going to dispatch a new thread that calls completed, and then this one goes all the way back and returns, right? So they cut the stack at a certain point in order to avoid the stack overflow. It's a bad solution, performance-wise. And we measured this in the Jerry project. It just kills the server, so not good. So the Servlet expert group is made of a bunch of very smart people, and they come up with something different, which is this. They said, okay, let's put the request in a synchronous mode, so start the sync like before. Then we add this new method, setWriteListener, okay? And we add this new interface, which has a couple of methods, but the most important one is this one. It's onWritePossible, okay? And it works in this way. The container calls this method when it knows that you can write stuff, and it will not block, all right? So when the container knows that it's ready to write and it can write without blocking, it calls on WritePossible. Then inside we have a loop. Very interesting. Why? Because we don't have recursion, we don't have callback hell, but we just have a very simple loop. The loop calls this new method, is ready, and says, hey, output, are you ready to write? Yes, I am. Okay, let's read something from somewhere. If it's not now, let's write it back, okay? And then loop, and say, are you ready to write some more? Yes, okay, so let's read some more, write some more. Are you ready again? Yes, read some more, write some more. Ready? No, I'm not ready, go out. When it's not ready and goes out, the container contract says, okay, when you are ready again, call again on WritePossible. We enter again from the container, right? So imagine you're writing to a slow client. Okay, you write, you fill the buffers, and at a certain point the buffers are full. The next write that comes says, I can't write, all right? So it blocks everything. So is ready at that point returns false and say, yeah, sorry, can't write anything more, right? But the container knows that it blocked because it's the container that actually does the write, right? So the container knows, I can't write it all, right? So I know, the container knows that I have to call you back. So let's wait for a while until the client can actually drain those buffers. And then when I get an event that I can write a little bit more, I'm going to call you back on write possible, right?
How does the container knows when the client is ready?
It knows because there is an NIO event that tells the container so. Okay? Yes.
You are creating an object first, right?
Say it again?
You are creating a new instance of write.
Well, it depends. I mean, this buffer here could be reused. Like you can allocate outside the while loop, and then you can pass it here as a parameter to be filled.
I mean the write listener.
No, this one is the do get. So you get, yes, this write listener gets allocated once per request, but not once per write, like it was before with the callback. Okay?
Yeah, but once per request, yeah.
Once per request, you have to allocate this object. However, these objects here, if they are stateless, they can be pre-allocated at the servlet level, and they just work. Because the only thing that they need, basically, this,
Would be tricky.
no, it'd be tricky, yes, because he actually needs the output stream from the response, which is specific for that particular request. So yeah, no, you can't allocate this guy. But yes, we have an allocate per request, so it's kind of unavoidable, but no per write. That's a good thing. So what do we get here? So is that clear? How does it work? It's a loop. You see inside the loop there's no allocation needed. Every time we go write, this buffer could be pre-allocated outside. There's no allocation. It's just a while loop. It's iterative. It doesn't blow the stack. No callback hell. Great. Okay. When we're done, reads from somewhere says, oh, okay, I have nothing more to give you, right? So it can return null, and then we just complete the response to the client. So very good. It's iterative, asynchronous writes now, and we're really on the right path. Very efficient, no allocation, no thread dispatches. Incompletes write go, as I said before, they do some iteration, then eventually is ready returns false. We exit the loop, eventually the container calls us back, we continue, and eventually at the end we return. Very easy, that's a smart idea. I mean, it's like, oh, we solved in one shot the callback hell, the allocation problem, and it's a very efficient API. I mean, a server like Jerry, when we are implementing this, we can do it in a very efficient way, and that's very important for a server. Not so easy, and now comes the fun part, all right? So how this API can be really tricky to use. Okay, so this is case number one. We have on write possible. We say, well, we have just one big buffer to write, okay? And we just write it. That's it. We have nothing more to write, okay? And then we have logger debug. Have we written this guy? Yes or no? And we call out is ready and say, well, if it returns true, it means that the whole content was written. If it returns false, it means, it'll take a time to be written. Well, where's the problem, though? Can you spot it?
You write something.
No, that's the problem.
Everything.
Yeah. Is ready. When it returns false, what happens? That tells the container, hey, you gotta call on write possible again. So what do? You write all content again, right? So it's not good. So now starts, making the idea that writing must be, guarded by some kind of condition where I have to test out is ready before writing stuff or after writing stuff, right? So, and this is very important. So let's try to fix this issue and, write this other example. On write possible gets called. Now I have a condition before I do the write, right? And I say, okay, is data available to be written? Maybe I need to fetch data from a REST service or something. And then I call, well, if I have data and the output is ready, then I can write that data. Okay, this could be even a while loop or something, right? What is the problem here? The problem here is this, that now isReady is not really like a getter method that has no side effects. It has a very important side effects. If it returns false, it schedules a call to onWritePossible. So now the order of these two expressions here is important. If you revert, like if you invert out isReady and then you call data available, it has a different meaning. In particular, what happens here is that in the previous case, like this one, if data available returns false and say, oh, there's no data, okay? You got called by the container, you say, I have no data, sorry. So you return, right? But you didn't call out isReady. So who's gonna call onWritePossible again? Nobody, right? So you're just stuck in there. So it is really important to understand what isReady does. isReady is it's the key concept of Servlet 3.1. When it returns false, it schedules a call to onWritePossible. So you always have to test for this.
You have an nested coupling of out isReady and onWrite.
I do have an nasty, yeah, that's not how to write code in the Servlet 3.1 API. But even the method isReady hints at just a Boolean property that you can read that has no side effects. I mean, I read it can return true or false, but that's it. If I call it multiple times, I can do isReady with a normal getter. What you will get is you're just calling multiple times this guy, but who cares, right? It's a simple getter. But here is not a simple getter. So they could have come up with a better name for this guy. Maybe just not call it isReady, but maybe just ready. That would have hinted that it's not really a query method with no side effect, but they didn't choose to do that. So, it was a discussed and heated discussion, but eventually came up in this way. All right, now I think I got it. Right? So onWritePossible gets called, out isReady. If it's not ready, I return, but I schedule for coming back. So now we're good. And then I do, but if I'm ready, I'm going to write this down. I mean, few bytes, right? Well, the problem here is that the first write, even if it writes just 1 byte or a few bytes, like in this case, may be pending. Like you write, and then you're not ready anymore, because you just blocked, right? So you can't write this other guy. It throws, a container says, sorry, you asked me to write that more, but, I haven't even finished the previous write, so boom, it just throws you an illegal state exception to you. Not only that, even if the container is able to write, probably the right behavior here is to throw an exception anyway, because you're using the API in the wrong way, right? So that's not good. So you gotta call isReady after every write. All right, I got that. So onWritePossible, out isReady, write the first chunk, out isReady, write the second chunk. What's the problem now? That if the second one returns false, then onWritePossible is called again, and you write the first chunk again, right? So it's not that easy to use it. I mean, the pattern that comes out here is you gotta go with a loop where you call for isReady, and then you gotta do one single write inside that loop. If you do multiple writes, you get it wrong. You write content multiple times. So that's the pattern. isReady, one write. That's it. This one is more subtle, and it goes in this way. I read something from a file, like for example, you're serving an image, right? Get a request for an image, read the image from a file, write down to the client. Okay, so I have a buffer, I read into the buffer and say, okay, I read a bunch of bytes here, then I have this while loop and a single write inside. That's a good thing, okay? So I'm ready to write, let's write this buffer. And then I say, well, you know, as a small optimization, let me peek into the file and say, well, if I'm, you know, let's see if I'm at the end of the file. If I'm not, you know what, I'm going to pre-fill this buffer again, so I'm ready for the next call of the iteration here, right? We go up, we're ready, we write the buffer, read again, out is ready, write the buffer, read, and so forth, right? So that's how I write the image. It's a large image, small buffer, okay? Well, and when I'm at the end, I just call context complete. Now, what is the problem here? The problem is that when you call write, after it, the call to is ready may return false, okay? The write may be pending. At that point, imagine this. You get the bytes from the file, then you try to write them, and then the system, the container says, oh, sorry, can't write. I haven't written any of these bytes. Now you take the same buffer, you pass it again to the file, you fill it with new data, right? And then you loop here and you say out is ready, and says, no, sorry, I'm not ready. So you go out. But now you have totally overwritten the first part that has not been written yet, okay? So the key point here is that write, when you pass a buffer to write, you don't own the buffer anymore. The container does. So you cannot touch the buffer until you actually test for is ready and that guy returns true. I'm done with the write, okay? So it's a tricky thing, but it is important. Well, the writes, as we know, throws exceptions. So typical pattern is try catch, response and error, 500, right? So couldn't load from the file system or whatever. What's the point here? All seems to work. I mean, if I put like a correct while loop here, then I'm good to go. No, because send error is blocking it, right? Send error actually calls, you can configure for an error page in your web.xml and then goes there and fetches a page and then writes that page in a blocking way down to the client. So you're actually mixing a synchronous and synchronous call, and that's not going to work, unfortunately. So you can't mix this. So what is the solution here? The only solution here is that you have to call response.setStatus500 and give up on the feature of custom error pages configured on the container. You have to kind of write your own stuff. But don't do this. Probably in Servlet 4, the expert group is going to fix this along with many other things.